Yeah, thanks, Christine. Yes, so I'm Fabian Zaiser, and this is going to be the first of 2 talks about generating functions for exact inference for discrete probabilistic programs. But we're going to set a different focus, so both of the talks should be interesting to you. Okay, let's start with a motivating example. Suppose your coworker gets 10 calls per week on average, and 20% of those calls are scams. And at the end of the week, your coworker is surprised that they only got 1 scam call. And the question is, what is the posterior distribution for the number of calls? And as we like to do, we can write a
Sorry to interrupt. Can you share your actual screen on AirMeet, please, if it's possible?
Sorry about that. I thought it was sharing.
Okay, thank you.
Thanks for letting me know. Okay, so this is the probabilistic program we care about. Just to explain it quickly, so X is the number of calls, which is sampled from a Poisson distribution with rate 10. And the number of scam calls is binomially distributed with success probability 0.2. And we observe the number of scam calls to be 1. So this is a simple enough program, so we might want to ask for an exact solution for the posterior distribution. And there are some tools for exact inference, so let's try them. First, we can try dice, but that one only supports finite discrete distributions, and the Poisson distribution has infinite support, so that doesn't work. Next, we could try SPPL, but that one requires that parameters of distributions must have finite support. And the X parameter of the binomial distribution has infinite support, so that doesn't work either. And finally, we can try the PSI solver, but that one outputs a symbolic expression that involves infinite sums. So that's also not very useful. So what's the issue with this program? The issue is the infinite support. Because if we just look at this fragment, the first 2 lines, and say we just want to compute the probability of y being 9, then we have to compute this infinite sum over possible values of x, because y depends on x. And of course, we cannot compute infinite sums exactly if we use probability mass functions. Okay, so what I want to talk about now is a method of solving this problem in particular, but also more generally all kinds of probabilistic programs in a certain language, which I will explain now. So the language we care about is an imperative language with a fixed number of variables, which take values in the natural numbers. What can we do with them? We can do affine transformations, where the coefficients are natural numbers again, to ensure that the result is a natural number. We have branching based on comparisons of variables with constants. And of course, we have sampling. We want it to be a probabilistic language. And we support the most common discrete probability distributions. And in places where it makes sense, we also allow the parameters of the distribution to involve random variables. For example, in the first parameter of the binomial distribution. So these fragments were already explained by Lutz Klinkenberg, who's going to talk after me, in a publication in 2020, how to handle those. And our contribution is to add conditioning, meaning observing events of the form a variable, of comparing a variable with a constant, and normalization, Bayesian inference, particularly as a language construct, which means we can also only normalize a part of the program, not just the whole program. And it turns out that Lutz Klinkenberg had a similar idea. This is why there's 2 talks about this. Yeah, so this language might seem simple, but it can express interesting models. For example, Bayesian change point models or models that biologists use to model animal populations. Okay, so how can we do exact inference for this language? The key is probability generating functions. And in case you don't know what that is, a generating function for a random variable is defined as a function that takes little x to the expectation of little x to the x, where x is the random variable. That's the general definition. But for discrete random variables with support in the natural numbers, we can also express this as a power series, where the coefficients are given by the probability masses. Again, we have an infinite sum here, but the key is that a lot of distributions have a closed form for this. And here are 2 examples, the binomial distribution and Poisson distribution. So how do probability generating functions help us for exact inference? Well, the idea is to represent the distribution over states in our program, where states mean the values of all the variables, to represent this distribution as a generating function. And each command in the language will transform the generating function describing this distribution. So we might start with some distribution g, and then we run the command, and there's a way of describing the generating function we get out. Important is that the closed form is preserved for all the constructs in our language. And also importantly, to evaluate g, we don't need computer algebra, but it's enough to just have automatic differentiation. Why do we need automatic differentiation? One example where we need it is the observe construct for conditioning. So if we observe a variable to be equal to some constant c, that corresponds, if you think of the power series representation of a generating function, to just keeping the terms involving x to the c. And that means we have to compute Taylor coefficients, and that involves derivatives. So if we observe c, it's the cth derivative. So if we observe very high numbers, like 100, that means we have to compute the 100th derivative, which will become important later. OK, so we get a PGF at the end describing the distribution, the posterior distribution. How does that help us? Because usually we care about other properties of a distribution, like the expected value or the probability masses. Well, it turns out we can extract those from the PGF. For example, the probability masses, as I said before, are just the coefficients of the power series. So if we do a Taylor expansion, we can get those back. Taylor expansion at x equals 0. The expected value can also be computed. For this, we have to take the derivative at a different point, namely at 1. And also the variance in higher moments can be expressed in terms of higher order derivatives at the point 1. OK, let's see how this works for the simple example from the start. So we start with a generating function that represents all variables being set to 0, and that function is 1, constant 1. And let's run through each of the commands in the program. First, we sample the Poisson distribution, which has this generating function. Then we sample the variable y, binomial, which leads to this change. I don't expect you to understand all the details. This is just to give you an impression. Next, we observe, which means we have to compute the derivative, which turns out to be this. And at the end, we normalize, which means we have to divide by a constant, and this constant can also be computed from the generating function. We can extract information from this result. For example, we can compute the posterior probability of the number of calls being 10. And for this, we have to compute this 10th derivative, and we get this result. And we can also compute the expected value, which turns out to be 9. So this was a simple example, but we can also support more complex ones. So this is, on the left, this might seem intimidating. You don't need to understand the details. Just basically, this models an animal population over several time steps. We might have some new arrivals, some survivors with some probability distributions. And in each time step, we observe some animals. So in the first step, it would be 0, and then 12, then 24, and then 21. So it means we have to compute quite high derivatives. But as you can see on the right, if you run the program, it will output the probability masses for the population at the end, and the expected value and variance. And it takes just over 1 second. So this can be efficient for some models. Maybe some notes on the implementation. The computation of the derivatives is the bottleneck. And we try to avoid computer algebra in favor of automatic differentiation because it's faster. I tried to use existing automatic differentiation frameworks like PyTorch, but that turned out to be very slow for higher order derivatives. So I ended up with a manual implementation of autodiff. But I found out that it's even better, instead of repeatedly taking the derivative, to just compute with Taylor expansions directly. OK, let me quickly talk about the limitations. In terms of language features, we only support affine functions. We only have comparisons between variables and constants, so we can't compare two variables. And we only have discrete distributions. This is all to ensure that the closed form of the generating function is preserved. And we don't support loops or recursion, but Lutz Klinkenberg might say more about this in his talk. In terms of performance, the size of the generating function can grow exponentially with the constants appearing in the program. So in the worst case, it takes exponential time. But as you saw in the example before, it can also be quite fast. Yeah, thank you for your attention. And as a takeaway, remember that generating functions can represent even distributions with infinite support compactly, and they are thus an interesting and powerful tool for exact inference in probabilistic programming. Thank you.